We can coarsely divide mathematical theories into two kinds. One kind of theory is trying to capture properties of a specific structure, so like N or R or the Euclidean plane, etc. So here we'd have a specific structure. Other theories, on the other hand, collect important properties that many structures share, right? So like groups, rings, fields, partial orders, or graphs. On the top part, we usually work with complete theories, right? So for example, if we just take the theory of the natural numbers or the theory of the reals over a fixed language, right, that results in a complete structure. On the lower part, we usually or often have theories that are incomplete, and this is completely intentional because we really want to capture only a certain property, important properties, but not all properties of a specific structure. We want to collect properties that the structures share. So like groups or rings, leaving other properties open. Property that complete theories have is that they impose the truth behavior, the same truth behavior on all their models. So more precisely, all models of a complete theory satisfy the same sentences. And that gives rise to the following definition. If we have two L structures, M and M, they are called elementary equivalent, written as M elementary equivalent to N, if for all L sentences sigma is satisfied in M, if and only if sigma holds in N. And it's not hard to see then that two structures are elementary equivalent if and only if they have the same theory. And as usual, I recommend you sit down and verify this briefly yourself. It's similarly easy to show that T is complete if and only if any two models are elementary equivalent. That almost follows straightforwardly from the definitions. It's also not hard to see that if two structures are isomorphic, then they're elementary equivalent. The reason is simply that if we have an isomorphism, let's say pi, then we know that a formula phi with assignment a1 up to an to the free variables holds in M if and only if the same formula with the assignment now pi of ai to pi of an, right, holds in N. Right? And since we're only interested in sentences here, that follows then automatically from the isomorphism property. We can get the converse of this for finite structures. So if M is a finite structure, then indeed N is isomorphic to M if and only if N is and M are elementary equivalent. In fact, if you remember, let's say for example that if we look at finite languages, right, we knew that there existed a single sentence sigma, right, that captured the isomorphism property for M, right? So that said that N is isomorphic to M if and only if it satisfies that sentence sigma. The reason for this was that we could first of all include in sigma a subformula that said that the structure has exactly cardinality of M many elements. And then we added also all the properties that hold given by the relation symbols in M and also the graph of the function of any function symbol interpretation in M. So this was if L is finite. If L is infinite, the proof is a little bit more complicated, so I encourage you to see how it would work in that setting. We've already seen that this equivalence between isomorphism and elementary equivalence is no longer true for infinite structures. So for example, we've constructed, using the compactness theorem, non-standard models of the theory of the natural numbers in the language of arithmetic, right? And these models are clearly elementary equivalent to the natural numbers because they have the same theory, right? But they are not isomorphic. Later, we'll also see that if we only consider the rationals under the order that they're given, so no algebraic structure included, we'll see that this is elementary equivalent to this same order, or the total order of the reals. But clearly, those two structures cannot be isomorphic because they don't even have the same cardinality. And we see directly also that elementary equivalence depends therefore strongly on the underlying language, because if I look at Q and R not as orders, but as, let's say, fields, they no longer are elementary equivalent. And one example that separates the two structures would be there exists an x such that x times x is equal to 1 plus 1. So R has a square root of 2, Q doesn't. We finish this lesson with a few questions that we aim to answer over the next few lectures. First is there a complete finitely axiomatizable theory with infinite models? So we've seen in the world of finite models that's not hard. But so far, all our examples for infinite models was just taking the theory right away, right? So for example, looking at the theory of n, and the question would be, is this finitely axiomatizable? The answer turns out to be no. But we could ask, are there other theories where we can just take a finite number of axioms and we get a complete theory? And this will indeed be the case, and we will see an important example of a theory is that of dense linear orders. Then we could also ask, right, we've seen that even a complete theory can have non-isomorphic models, right? And for example, in the case where we had, so we haven't proved this yet, but we will at some point, when we're looking at dense linear orders, right? And we saw that those, or I stated that these two structures here are actually elementary equivalent. Now we can ask this general question, right? Given a structure M, is there an n of a different cardinality or of any given cardinality that is elementary equivalent to that given structure M? And this will indeed be the case, and this will be the subject of the next lecture. Finally, we can ask, is there a theory that has, for a given cardinality, precisely one model up to isomorphism? So for example, we saw that the theory of n has non-isomorphic and in fact many non-isomorphic countable models. Now we can ask, is there a theory that for cardinality Aleph naught has up to isomorphism precisely one model? And again, it will turn out that the theory of dense linear orders will play an important role in that, answering that question.